All right, so we're going to continue our discussion of the singular value decomposition. And because I kind of had to rush at the end of class last time, I'm going to basically just go back over what the main components of the singular value decomposition are as a review. So A is going to be an m by n matrix. So this can be literally any matrix. It can be any shape, any size. It doesn't have to be symmetric. It doesn't have to have any nice properties at all. It can be any matrix you pick. Now what a singular value decomposition does is it gives you a way of splitting the matrix A up into the product of three matrices. Okay, U, sigma, so this is U, sigma, and V transpose. Where, so remember A is an m by n matrix. U is going to be an m by m orthogonal matrix. Okay, which means, again, an orthogonal matrix is a matrix that has orthonormal columns. So it's a square matrix with orthonormal columns. Sigma is going to be one of these sort of, I'm going to call it a pseudo-diagonal matrix. That's not really a term you're probably going to see anywhere else. Diagonal. Okay, and it's the size, it's going to have the same shape as A does. So it's m by n, okay? And what I mean by pseudo-diagonal is, so say A is like a 2 by, or let's say A is like a 3 by 4 matrix, okay? Then it's going to look basically diagonal. You're going to start sort of with your singular values on the top. So you're going to start with sort of in the top left corner, and you're going to write your singular values in. And it has the same shape as the original matrix A, but it's not a diagonal matrix because usually we think of diagonal matrices as being square. Okay, so this matrix doesn't have to be square. It has the same shape as whatever A has. All right, but the only entries in it that are non-zero are these entries that sort of start at the top left corner and move down. And finally, V is going to be an n by n orthogonal matrix. Okay? So it's an n by n matrix with orthonormal columns. So if you look at the shapes of all these matrices, we have an m by m times an m by n times an n by n. When you multiply these matrices together, you're going to get an m by n matrix like we're supposed to. All right? So I'm going to talk in a minute about sort of how you find these matrices. But first I want to talk a little bit about the geometric intuition behind what this decomposition is telling us. Okay, so if we think of A as giving us a linear transformation, A is going to give us a linear transformation, or let's write it like this. Say T of x is equal to A times x. That gives us a linear transformation from Rn to Rm. Okay? Now what this transformation looks like is, here's just sort of a little picture of, think of this as being Rn. Okay? And we can think of the matrix as sort of taking the vectors in Rn, and maybe it stretches some of them, maybe it rotates some of them. It just does can do a whole lot of things to the vectors in Rn. Okay, so remember this is Rn. It's going to disappear in a second, but so what we can do is we can essentially split the linear transformation defined by A up into three separate linear transformations. Okay, so maybe I'll write this down like this. So if A is equal to U sigma V transpose, then when I multiply a vector by A, essentially I can think of this as sort of being done in three steps. Okay, the first step is I multiply x by the matrix V transpose. Okay, and so the matrix V transpose sort of acts on x and changes x in some way. Then I can multiply the resulting vector by sigma, and that changes the vector even further. And then finally I can multiply the resulting vector by u, and that's going to do something else to the matrix, or to the vector. Okay, And so we can think of the linear transformation defined by A as actually being broken up into sort of 3 steps. Each of these steps is determined by one piece of the singular value decomposition. So what do each of these pieces do? Well, because V is, I'm going to actually copy this here so I can copy it onto the next slide. So because V is an orthogonal matrix, remember orthogonal matrices preserve angles, they preserve lengths of vectors, they preserve the angle between 2 vectors. So essentially they're just kind of like a rotation. They're sort of just taking all of Rn and it's rotating it in some way. So that is what V transpose is doing. That's what the first step of our linear transformation is doing. Sorry, I can't. I'm trying to paste that thing in here. For some reason, it's not letting me paste that in, so I'm just going to do this, okay? So the first step of the linear transformation, since V is an orthogonal matrix, V transpose will also be an orthogonal matrix. And essentially all we're going to see is that when we multiply by V transpose, we're just rotating the plane in some way, or we're rotating Rn in some way, okay? But the angles between vectors are being preserved, the lengths of vectors are being preserved, etc. Okay? Now the next step is multiplying by sigma. What does sigma do? Well, because sigma, let me write it like this, because sigma is a matrix like this, you know, it's one of these fake diagonal matrices, and it can look like a lot of things, like maybe you have zeros, you know, maybe the singular values don't go all the way down or something, whatever. But essentially, because most of the entries in this matrix are zeros, except for the singular values, when you multiply by a vector, what the singular values are going to do is it's going to rescale the vector by sigma 1 in the x direction. It's going to rescale it by sigma 2 in the y direction. Then it's going to rescale it by, like, say, 0 in the z direction. Okay? And so what happens with this second step when we multiply by sigma is we are taking sort of the coordinate directions, so like the x and y directions, and we're rescaling them. Okay, maybe making them longer, making them shorter, whatever. Okay, but in those main coordinate directions, we're doing some rescaling of some form. Okay, and the amount that we're rescaling by is determined by the sigmas, the singular values. Now at this step, because sigma doesn't have to be a square matrix, you also could be changing the dimension. So you might be going from like 3 dimensions to 2 dimensions, or 5 dimensions to 17 dimensions. There could be some change in dimension, okay? But those coordinate directions are always going to sort of be sent to the coordinate directions over here, possibly with some rescaling determined by sigma, okay? And looking back at our decomposition one more time, okay? The last step now is multiplication by U, and since U is another orthogonal matrix, it's going to preserve angles and preserve lengths of vectors and things like that. So it's just going to look like a rotation. Okay? And so this map, or this function determined by A, can really be split up into 3 functions, where each of these functions has a nice specific form. V transpose, the function determined by V transpose, just rotates Rn. Sigma rescales vectors, but only in the only in the coordinate directions. So it only sort of rescales in the x direction, y direction, and z direction. And that rescaling is determined by the singular values. And then what U does is it rotates sort of the final picture into the correct place. Okay. So this is the idea behind what the singular value decomposition is actually doing geometrically. Now, it ends up being a very useful theorem, and we'll see some applications probably. I don't know that I'll make a video of those because I think we'll probably have enough to talk about with our with the examples we're going to do. But I will talk briefly on Wednesday about some applications just to give you an idea of what can be done with this. So how do you compute the singular value decomposition of a matrix? Well, the first step is you want to compute A transpose A. From A transpose A, you can always find eigenvalues, and you can find orthonormal eigenvectors. All right? So you want to find the eigenvalues of A transpose A, and you want to find an orthonormal basis of eigenvalues. And that can always be done because A transpose A will be symmetric. Now, once you've found those lambdas, those eigenvalues, and you found those eigenvectors, then you actually have enough information now to build the sigma matrix. And the way that you build the sigma matrix is you take the square roots of those eigenvalues you found in the previous step. Those are your singular values of your matrix. And the singular values of your matrix are just going to be used, you're just going to place them on the diagonal of your matrix. Okay? And you put zeros everywhere else. And the shape of the matrix that you're doing, your sigma matrix, is just going to be determined by the shape of the original matrix A. So write down a matrix that's the same shape as A with all zeros, and then just start plugging your singular values in along the diagonal. So that tells you what sigma is. You can also build the V matrix, because these eigenvectors you found in the first step, these orthonormal eigenvectors, are going to be the columns of the V matrix. Okay? So you just plug those in. That gives you your V matrix. Now, to find your U matrix, you have to do a little bit more work. But the way this is done is what you're going to do is you're going to take, so if you remember from last class, let me make this a little bit thinner there. Okay. So I have my orthonormal basis of eigenvectors. Okay. Now, my singular values, some of them might be 0 and some of them might be non-zero. So maybe say sigma 1. Sigma 1 is like our biggest one, then sigma 2, all the way down to say sigma r. Suppose these ones are all bigger than 0, and then everything after the rth one, suppose that's equal to 0. Okay, so the first r singular values are bigger than 0. The last n minus r are all equal to 0. Now, what you're going to do for the first r of these vectors here, okay, so you're not going to do this to all of the vectors, but only the first r, the ones that correspond to non-zero singular values, you're going to take those vectors, you're going to multiply by a, and then you're going to divide by sigma I, the corresponding singular values. Now, because we're dividing by sigma I, that's essentially why we can only do this procedure for the vectors that correspond to the non-zero singular values. Right? You can't do this for the vectors that correspond to the zero singular values. So you take your v vectors, you multiply by a, and then you divide by the corresponding singular value, and that's going to give you, so if you do that to say v1, that's going to give you u1, which is going to be the first column in your U matrix. If you do that to v2, that's going to give you u2, which is going to be the second column in your U matrix, and so on. Now, there's one problem here, and that problem is that sometimes you won't have enough singular values. Sometimes you won't have enough non-zero singular values to sort of build the matrix U to its full size. So remember that U is supposed to be an m by m orthogonal matrix. So if the number of non-zero singular values you get is less than m, then you're not going to be able to get enough U vectors in this way. Okay? And so in that situation, what you have to do is you take the U vectors that you did get using this procedure, so you plug those in that order. Okay? And then say you need 2 more. Well, what you can do is you need to essentially just find any vectors, say UR plus 1 and UR plus 2. In this case, suppose you're just short 2. You just need 2 more. Okay? Well, you can find any 2 vectors you want as long as those 2 vectors sort of fill this out to give an orthonormal basis. So these 2 vectors have to be orthogonal to the vectors you already found. They have to be orthogonal to each other, and they have to be unit vectors. Now, I'll show you some tricks for how to do this, so don't worry if it's not clear immediately how to do this. But again, the idea is that this formula will give you R columns, where R is the number of non-zero singular values. If that's not enough to build up an orthogonal m by m matrix, then you have to sort of figure out what the other columns are going to be. And any columns you pick that are orthogonal or that sort of complete this into an orthonormal set will work. Okay. So again, we'll kind of talk about how to do that. So that's the fifth step, is that we have to take the UI that we already have. We have to expand them to an orthonormal basis for Rm by adding m minus r vectors if necessary. Okay. Then once we do that, once we have those vectors, we can plug them in to get our U matrix. All right. So quick review: A is an m by n matrix. A transpose A is going to be symmetric, and the eigenvalues are going to be non-negative, with corresponding eigenvectors v1 through vn, and these things are going to give you an orthonormal basis for Rn. The singular values are going to be precisely the square roots of these eigenvalues. The decomposition we're looking for is this: A equals U sigma V transpose, where sigma is one of these sort of pseudo-diagonal matrices that has the same size as A, and the entries on the diagonal are going to be the singular values. V is going to be an n by n orthogonal matrix with columns v1 through vn. And U is going to be an m by m orthogonal matrix whose columns are given by these formulas, where we might have to fill in with extra vectors to get an orthonormal basis if we need to. So I'm going to stop the video here. I'm going to make separate videos with some examples of this. But this video was just sort of to give you an overview of what we're going to do and how we're going to do it. But stay tuned for the following videos, which will show you some examples of actually doing this procedure.